Hello again. So I'm back doing this problem that I said I was going to do for horizontal asymptotes. F of x equals 3x subtracted by 1 over x squared minus x minus 6. So I'm going to go ahead and do that. Now there's a few pieces of information that are going to help me be able to graph this. At least try to create the most accurate graph that I can. I'm not going to use a graphing calculator, although usually, if it was a graphing calculator class, I'd suggest use your graphing calculator. But actually there's times where I give this type of a problem, I say no graphing calculators, just do the best you can. And students usually think it's impossible initially, but as long as you have the right steps, it's okay. And people have been doing this for hundreds of years without a graphing calculator, so it's good to practice that too. So I got this function of a polynomial divided by a polynomial. I know it has a horizontal asymptote because the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 1, degree of the denominator is 2. So bam, I know I got a horizontal asymptote. And since it's less than in the numerator, the degree that is, I know the horizontal asymptote is at 0. No problem there. So the horizontal asymptote equals 0. Now I got to check for vertical asymptotes too. And basically what that means is, well, is there any x values I can substitute in that are going to make my denominator 0? And there's a couple ways you can do it. You can use the rational zero theorem. I wouldn't recommend that for such an easy problem. And you can use completing the square, and I suppose you can use the quadratic formula. But fortunately, all you really have to do is factor this bad boy out, and you'll find that it's not that difficult at all. And x squared minus x subtracted by 6 factors into x minus 3, x plus 2. And if I use the zero product property, I say, okay, what's going to make the x equal 0? Well, if I substitute in a 3, it'll make this value 0, or if I substitute in a negative 2. The other way to think about it is just take the opposite of this sign, just take the opposite of this sign. So it's got two vertical asymptotes, two x values that will make the denominator equal to 0, and they are at 3 and at negative 2. It's not 3 comma negative 2, actually maybe I should rewrite this. It's 3 and at negative 2. So don't say, oh, it's at the point, no, it's 3 and negative 2. There's a few other things that will actually make this problem a little bit easier to solve. And what that is figuring out what the x-intercept is and what the y-intercept is. And in my opinion, the y-intercept is much easier to solve, so we're going to do that one first. If you want to figure out what the y-intercept is, just set all the x values equal to 0. So you got 3 times 0 subtracted by 1, 0 squared minus 6, 0 squared minus x minus 6. What I like to do is I say, okay, everything with an x is 0, so I don't even have to account for that. All I got is negative 1 divided by negative 6. And you can substitute them in if you want to, but it's going to come out to the same thing. So I got negative 1 over negative 6. So it's a sixth, 1/6. So my y-intercept is 1/6. If I want to, account for the actual point on the graph, well, my x value is 0, and my y value is a 6. That's what a y-intercept means. It's like, if the x value is 0, where does it hit the y-axis? There. X-intercept is a little bit more difficult, but not really, actually. What I do is I set my y equal to 0. My y is f of x. So I'm going to do that, and if I want to think about it theoretically, but what I tell my students is just say, figure out what's going to be true here. Just set the numerator equal to 0 and solve it. But students say, I don't get it. So what I do is I say, okay, if you cross multiply 0 in this, denominator is canceled. No need to even worry about that. So that's why I don't even worry about the denominator. So I set my y equal to 0, and I say, okay, 0 equals 3x subtracted by 1, solve for x. And you're going to get your y-intercept. Add 1 to both sides, divide by 3, x equals a third. Or it's a third comma 0. You can say the x-intercept is a third, the y-intercept is a sixth, or you can write it in coordinate form, 1/3, 0, and 0, 1/6. Like I said, I don't know if this graph's going to be perfect. I would hope that it's as good as possible, but I'll try my best. But after you do these graphs, thousands of times, you get a pretty good indication of what's going on. So, if I want to do this correctly, first of all, I want to account for my vertical asymptotes, which occur at 3 and at negative 2. So at 3, there's no graph. There's no graph that exists. And at negative 2, there's no graph that exists. That's the whole definition of a vertical asymptote. It's not going to, hit this point at all. But what's really interesting is I know in a vertical asymptote, it's either going to approach up or it's going to approach down. So that's pretty cool. Like, I didn't even have to do any work as long as I understand that aspect of it. The x-intercept, where it hits the x-axis, is at a third. Here's 1, a third is like 0.3333, so it's like right there. Not perfect, but what are you going to do? And the y-intercept is at 0.6, so a sixth of this is like right here. Still not perfect, but again, what are you going to do? Last thing I want to talk about is the horizontal asymptote. The horizontal asymptote is at 0, which means as my graph continually goes this way, towards negative infinity, or continually goes this way towards infinity for my x values, what's going to happen is my graph's going to like approach like this. It's going to kind of hug the x-axis but never actually touch it. Same thing here. That's not saying that it never actually touches the x-axis, because what it could do is do something like this and then not touch the x-axis. That's something that students always have to watch out for. But in this particular graph, it seems like it's, pretty common sense. The last thing you would do, if you wanted to do this without a calculator, is make yourself a makeshift table real quickly. And I'm not saying, substitute in values over and over again, because that's boring and it takes too long. What I want to do is basically figure out what some values are on this interval of the graph. This is a specific interval from negative infinity to negative 2. From this interval, negative 2 to 3. And from 3 to infinity. Now, you just want to check some points really quickly. And when you do that, you kind of get an indication of where you're going. Okay, it looks like it's going up, but I want to verify really quickly. I want to make sure it's not like doing this and this. I'm pretty sure it's going like this, and I think it's going to go like this, but what I want to do is put a testing point in. Now, I can either test 1 or 2, and I'm going to test 1, because it's easier. I could test in 2 into this, but putting in 1's going to just be easier for me. So if I put the point in 1, I have to plug in the point 1 into this equation. So this is 3 minus 1, which is 2. And this is 1 minus 1, which is 0, minus 6, which is negative 6, which reduces to negative 1/3. So when my x value is 1, my y is negative 1/3. And I mean, if this was the only problem you had, like on a 20-minute quiz, you'd actually, take more care to do this. YouTube videos are 15 minutes, so I can only go as long as that. And I'm not going to anyways. So my x value is 1, my y value is like a negative 1/3. Okay, so I can try to plug in negative 1, I can plug in 2, but I'm fairly confident, I hope so at least, I'm fairly confident that the graph is going to do something like this. It's going to, keep going down and approach negative infinity, but never actually touch this line, and it's going to go upwards like this. Like I said, that's speculation, but it's confident speculation, hopefully. What I want to do now is test a couple points in this interval. I can't test negative 2, it's not going to work. So I'm going to test negative 3 out. And when I substitute in negative 3, I get negative 9 minus 1, which is negative 10. And negative 3, that's 9, minus negative 3, that's 12, minus 6 is this. So it's like negative 5/3. So negative 5/3 is like negative 1.6666 repeating. So it's like, like right here. I just want to make sure, just see what's going on. I think what's going to happen is it's going to go like this, but you can never be too sure. So let's test out the point negative 4. And when I test that out, I get negative 4 times 3 minus 1 is negative 13 over 16 minus, that's 20 minus 14, negative 13 over 14, which is like negative point, I don't know, it's like negative 0.9 something. So it's got to be closer here. Okay, that's my speculation. What's going to happen is it's going to go like this. I don't actually think it's going to cross and then come over like that. I actually think it's probably going to do this, because what I'm tending to see right now is that this value right here, based off of these two, is going to become a larger negative, and your denominator is going to become a larger positive number, which means that it's going to get ever and ever and ever and ever and ever closer to, actually, well, I shouldn't say larger negative, but what's happening is that this number seems to be going down, technically negatives, and this number tends to be going up. So what you're doing is you're kind of approaching that value. Yeah, but this one's going to go up much quicker. So it's going to be very close to -0. Yeah, that makes sense. Yeah, that one's going up much faster. Anyways, I'm rambling there. Continuing along, so let's say I want to have a testing point of 4 and a testing point of 5. So if I do that really quickly, if I substitute in 4, I get 12 minus 1, which is 11, and 4 is 16, minus 4 is 12, minus that is 6, so it's 11/6. I should have put in these values too. -13 over 14, -5/3. So 11/6 is almost 2. It's like 1 point, you know, and then, I don't know, like 1.8 something. So, almost. I'm sure I can figure that out. I'm going to say like 1.83, but I could be wrong. Okay, the next one is, let's test out 5 really quickly because I want to see what's happening. Is it going down? Well, it's got to be going down, and that's clear at this point. 15 minus 1 is 14 over 25 minus 5 is 20 minus that is 14. So it's 14 over 14, which is 1. Whew, finally an easy one. So I'm taking a guess that it's going to go like this. I don't think it's going to cross under and come back up. I just think it's going to do this and kind of go like that. So that's a very makeshift graph without a graphing calculator. People would say, well, why did you waste all that time? Why didn't you just, you know, just put in the answer? But I thought it was pretty fun. I think it's pretty cool. If you're ever asked to do this without a calculator, figure out your horizontal asymptote in this particular problem, if it has one. Vertical asymptotes are incredibly important because you can see what happens. And don't forget the value of trying to figure out the x and the y-intercept. So we did that. I think we'll do one where we have an example with an oblique asymptote because I think that'd be pretty cool. Other than that, have a good day for now. Goodbye.